Hello everyone, welcome to my channel MacPandit Learning Hub. In this session, we will talk about the acceleration analysis and mechanisms using graphical vector approach. In the previous sessions, we were mainly centered on the velocity analysis and mechanisms. Now, we will see how can we calculate the acceleration of different points on different links in a mechanism using the graphical vector approach. So we will start with basic definition of acceleration. So as we all are aware that acceleration is the rate of change of velocity with respect to time. The direction of acceleration is defined by the direction of change in velocity. The change in velocity is possible either by change in magnitude or by change in direction, or both the change in magnitude as well as direction. Now let us see how can we conduct the acceleration analysis of a link. So here we are going to consider a link OA of length r rotating at an angular speed of omega and at an angular acceleration of alpha at time t. Now we will observe the motion of this point A on this crank OA after time t plus delta t. Now we will see how can we calculate the acceleration of a point on a link. Let us consider a link OA of length r rotating at an angular speed of omega and at an angular acceleration of alpha at time t. Let us see if we are interested to calculate the acceleration of this point A, then how can we do that? We will observe the motion of this point A after time t plus delta t. So let us assume after t plus delta t time, the link OA, it acquires the new position OA prime, right? In the velocity of point A, it changes from VA to VA prime. Now here you can see the velocity is basically changing in two directions. So one direction is perpendicular to this length OA and another direction is basically parallel to this length OA. So you can see here one component of velocity vector, it is perpendicular to this length OA, and another component of velocity vector, it is parallel to this length OA at time t plus delta t. That is, the change in velocity, it is happening in two directions. So this indicates that acceleration of point A relative to this point O. So just note it down that this point O is basically a fixed point. That means the link OA, it is pivoted at this point O. So acceleration of A, it will have two components, again one perpendicular to A, another parallel to OA. So the acceleration component which is perpendicular to OA, this is called as tangential acceleration, very important. And the acceleration component which is parallel to OA, we call this component as centripetal or radial acceleration. Now let us see how to calculate the magnitude of these two components. So first we will talk about the tangential acceleration component. So the velocity of A perpendicular to OA at time t is equal to VA equal to r omega. Now velocity of A prime at time t plus delta t, this is given as Va prime equal to omega plus alpha delta t multiplied by r. So this is very obvious. This is nothing. This is basically the change in velocity during the time delta t. So delta omega divided by delta t, it is nothing. It is simply equal to alpha. So we can write it down, velocity of A prime at time t plus delta t, that is Va prime equal to omega plus alpha delta t multiplied by r. Now velocity of A prime perpendicular to OA, it will be given by Va prime cos delta theta. So that means this is the component, right, along the horizontal direction which is perpendicular to this length OA. So now we can resolve this Va prime vector along the horizontal and vertical directions. So we can see here the component which is perpendicular to length OA is Va prime cos delta theta. Similarly, change in velocity perpendicular to OA, it can be very easily calculated by simply subtracting the velocity at time t from the velocity component at time t plus delta t. So this will be Va prime cos delta theta minus Va. Now we can define the tangential acceleration of point A, which is perpendicular to OA. It will be given by Va prime cos delta theta minus Va divided by delta t, and again we will put limit delta t tends to 0. So in that case cos delta theta will tend to 1, and finally we can solve this and we will get the final relation as r alpha. So just remember, this is the magnitude of tangential acceleration component, right? And obviously the direction in this case will be perpendicular to OA, and again the sense of this vector, you can say it will be towards right. So we are going to denote the tangential acceleration component by this notation, that is acceleration of A relative to point O, this is equal to r alpha, and then we will put a superscript t to denote the tangential component of acceleration. Now let us move ahead and let us see the magnitude of centripetal acceleration. So obviously the centripetal acceleration, it will be given by the change in velocity in a direction parallel to OA. So let us see what is the change in velocity in a direction parallel to OA. So obviously the velocity of point A, that is Va, is equal to 0, right, at time t. So just remember, right now we are talking about the direction parallel to length OA. Similarly, the velocity of point A, that is Va prime, at time t plus delta t in a direction parallel to OA, this is simply equal to Va prime sine delta theta. Now the change in velocity, it will be given by Va prime sine delta theta minus 0, and again the acceleration of A parallel to OA. Now what we are going to do, we are going to simply substitute the value of Va prime, that is omega plus alpha delta t, right, into this expression, and finally we will get this final relation. So omega plus alpha delta t r sine delta theta minus 0, obviously, divided by delta t. Now as we take the limit delta t tends to 0, so sine delta theta will tend to delta theta, and finally we will have the acceleration of A in a direction parallel to OA as omega r d theta by dt, and again this is nothing, this is the angular velocity component, so this will become omega square r. Now finally the centripetal acceleration component, right, it would be calculated as omega square r or v square by r. So this will be the magnitude, and the direction, we know the direction will be parallel to OA, and again the sense will be, this is very important, what will be the sense of centripetal acceleration? This will be from point A towards point O. So the centripetal acceleration component, right, obviously it will be pointing into this direction, in the downward direction. Now the centripetal acceleration component, we can denote it by FAOC is equal to omega square r is equal to v square by r. Now let us see how can we represent the acceleration of point A relative to O through a vector diagram. So now this is very easy. Again, what we are going to do, we are going to mark the pole point in the vector diagram. So this point O1, this is a fixed point and it is representing the pole of the acceleration vector diagram. Now from this point O1, we will first draw the centripetal component, that is FAOC. So we know FAOC, it is pointing in the downward direction. So the centripetal component of acceleration, this is pointing in the downward direction. So we are going to draw this vector first, and then finally we will draw the tangential component of acceleration, this is FAOT. So FAOT, we know that this is perpendicular to this length OA, and again the direction is towards the right side. So we will draw the next vector FAOT, something like this, and after that the resultant vector will be basically given by this solid line. So this is the resultant vector FAO vector. So obviously this is the resultant of two components, one is FAOC vector and another is FAOT vector. So here this O1A1, it is representing the acceleration of point A relative to O. Or we can also say that this is nothing, this is absolute acceleration of point A, because we know that point O is a fixed point. In order to differentiate the acceleration vector diagram from the velocity vector diagram, here we are denoting the alphabets O and A along with a subscript 1. And again, this intermediate point, it can be denoted with the alphabets OA. So this is nothing, this is simply acceleration of A relative to O. Or you can again write this thing something like this, AO. So this rests upon the convenience of the user, that which notation he wants to follow. With this, I like to conclude this session, and I hope to see you in the next session. Thank you.